So we've done a couple lectures on uncertainty analysis, right? The first lecture we did was design stage uncertainty analysis, and we were able to estimate how much uncertainty we would have in a result. I guess it was really an estimate of the minimum amount of uncertainty we would have in a result if we designed a measurement system in that way. Did you have any lecture notes?
Me? Nope. I was going to pull it up on my computer.
Okay, it is on Slack now. So the second lecture that we did, so beyond the design stage. The design stage was we took the spec sheet information and we estimated based on the resolution of the machine and the uncertainties and errors in the spec sheet, how much the minimum uncertainty would be in the final result once we designed or once we had an actual measurement set up. But we said that was just a preliminary analysis, right? That was sort of the minimum amount of error, and then when we actually had a measurement, we would have to adjust that value. Also, we discussed how error propagates from a measurement value that we have to a functional dependence on that measured value. So we talked about measuring volume and how if we measured the length of a side, how the uncertainty in one side length would actually propagate to the volume and how we would estimate that. And I can't recall if we did I meant to go back and double check because we had that sort of long break there. Did we start discussing this perspective yet? I don't think we did. So I think we're just going to start from the beginning and build it up. There's only 8 pages of notes, so no problem. Okay, so rigorous uncertainty analysis is the the type of uncertainty analysis that we would do if we were going to turn it in, right? Like this is the good one. So what we should do. I mean, the propagation holds true for design stage, and it also holds true for this rigorous uncertainty analysis. So we have learned about confidence from a statistical point of view. Now, some of this I took from the intro, and I moved it to this lecture because I think it fits better here. And it had been so long since we had talked about it. So based on sample variability, we might have p% confidence in a given measurement. As we have learned, an estimate of the variability of the random variable x, in this case the measurand, is given by its sample standard deviation, Sx. In the case of multiple samples, its best estimate was the sample mean of standard deviations. The best estimate of the value of x, that is, its mean, mu x, was the sample mean, x bar. In the case of multiple samples, it was the sample mean of sample means, x double bar. Finally, the best estimate of the variability of the mean was the sample standard deviation of sample means, which we often call just the standard deviation of means. We just drop all the sample, but it's really the sample standard deviation of the sample means. And this is the one that we're actually probably most interested in terms of our confidence intervals, because this is an estimate of how well we know what that mean value is. Okay, and often our measurement is, our best estimate of the measured value is the mean. So we care about how well we know the mean. So Sx bar is often of great importance to us. Further recall the nice estimate of Sx bar from a single sample with size n is given by this. So you take the standard deviation, the sample standard deviation, Sx, and you divide it by the square root of the sample size, n. Remember, this is an estimate of the standard deviation of the means, even though we only have one sample. So standard deviation of the means is the standard deviation of the mean from a bunch of different samples, right? So if you took the standard deviation of the mean of a bunch of different samples, which we did in chapter 4, we could estimate the standard deviation of the means. This is saying, and we saw this formula before, you can actually estimate that with only having one sample, and that's what this square root n is. So really nice little formula. We use it a lot. As we can see, as sample size increases, the standard deviation of the means decreases. This type of error in a measurement is called random error and gives rise to random uncertainty, UR, related to what we have called confidence intervals about the best estimate of the mean, such as for a single sample of size n, x is an element of the interval centered about x bar, the sample mean. It's t standard deviations of the mean plus or minus with p% confidence. Okay? So remember, you can use the t-score depending on how much confidence you want. So if you want really high confidence, your t-score is going to be larger and your interval is going to be larger, right? So this was our best estimate of a confidence interval for a value. The random uncertainty is a half interval. So you take essentially the plus or the minus of this. So t nu comma p, and then we actually put s here instead of sx bar. We're going to use s to be we're going to kind of redefine this to be a really common thing to use, lowercase s, which has a 68% confidence in terms of t. It's the normal, it's a standard random uncertainty, which is simply one standard deviation of the means. Okay. So this s is our standard random uncertainty, and it's often what we use all the way through our calculation until we get to the very end, and then we say, okay, this is for one standard deviation. We want to know for like 2 standard deviations or whatever confidence we want. So we use the one standard deviation, the standard random uncertainty, until that last step. However, error can arise from more than just randomness. Other sources arise that bias the measured value, say up or down from the mean. This is called systematic error and generates systematic uncertainty, UB, because bias. And systematic standard uncertainty, B, that has 68% confidence. So we're making an analogy here between S and B, right? So we're saying for random uncertainty, the standard uncertainty is S. For systematic uncertainty or bias uncertainty, the standard is B. Okay, one standard deviation is B. Let a measurement instrument's manual list an elemental error B in it. So just consider this, which, unless otherwise stated in the manual, is assigned a 95% confidence. We will assign a 95% confidence because that's a pretty standard value of confidence to give. So if you report in a manual an error, we hope that you would adhere to that sort of convention. So the systematic uncertainty then is B over 2, which is the instead of to 95% corresponds to 2 standard deviations of a Gaussian, and so 68% corresponds to 1 standard deviation of a Gaussian. So we wanted the 1 standard deviation, we wanted the standard uncertainty, B, systematic uncertainty, and so we had to divide big B, the 95%, the 2 standard deviation one by 2 to get to it. Assuming a large sample was used to estimate B, which we do always assume that, because unless we know otherwise, unless they say, oh, you know, this estimate is based on 20 samples, then or 20 measurements. Like then we know that n was 20, right? But unless they say, otherwise we just assume it was big. So remember, the reason we care about that is we care about estimating nu, the degree of freedom. And if the degree of freedom is greater than 30, it's pretty much just a normal distribution, just a Gaussian. The t distribution just becomes the z distribution, the Gaussian distribution at that point. So assuming a large sample is used to estimate b, we might report an uncertainty associated with that error to be ub equals 2b with 95% confidence. And we assume here a Gaussian distribution, but the distribution shape has little effect on the results. Let's consider systematic error a bit more. So we're going to do a little example here kind of in line. A scale might be systematically reading high. I think we might have talked about this one a little bit. Did we? You guys should know this. Anyways, I know my scale does, especially around the holidays. This is a joke. Does that joke sound familiar? Sounds familiar. I think what I did is I reused this from the intro because I felt like it's been so long since we talked about these different types of error and uncertainty that we probably wouldn't be remembering them. So I moved it in the notes to here for next time, but I thought you guys could use a refresher. So this is why I moved it here. All right. So this can be identified and mitigated by calibration to a standard. Nist calibrates weights. We talked about that. Let's say you have a 10 kilogram Nist calibrated weight. Such an object that you use to calibrate things is called a standard, with one normal standard deviation confidence plus or minus 200 times 10 to the minus 9 kilograms. Let's say I weigh it 10 times on my scale, and the sample mean is 10.5 kilograms. The sample standard deviation is SX. It's 0.3. The calibration allows me to adjust the bias on my scale by 0.5 kilograms. So you don't have to be stuck with that bias, right? Like you can calibrate your scale. So like if you're half a kilogram off, you can change there's almost always some way to adjust the calibration, right? So you adjust it so that it reads the correct value when you calibrate it. So 10 kilograms that you know is 10 kilograms or really, really close to 10 kilograms should read 10 kilograms if it's properly calibrated. So you can do that. You can adjust it, and that works. However, there remain two systematic uncertainties associated with my scale's bias. So Nist's standard uncertainty, so their uncertainty in the standard, right, in the 10 kilogram Nist weight, this one's super small, right? Which makes sense because it's Nist and they're like really good at it, right? So we trust their value, but like there's still a little bit of uncertainty in it. And our calibration standard uncertainty, which is if you take the standard deviation, which was 0.3 kilograms, divided by a square root of n, standard deviation of the means is our uncertainty value, so 0.0949 kilograms, which, is much, much larger than 200 times 10 to the minus 9 kilograms. So my scale, the measurement that I made, not as good as the Nist measurement. If we increased n a lot, we could get that to get smaller and smaller and smaller, though, right? So probably should do like n equals a gajillion, which is not a real number. I don't know if it's real or not.
It's real in this one.
It's giga plus million.
Is it? Yeah. Okay. I believe you. So Jay-Z would like it at least. Jay-Z would like it. The systematic standard uncertainties are combined in the usual RSS way. He cheated on Beyonce. The hell, man.
Why would he do that?
It's a really good album. But
I actually don't really have a strong opinion about Jay-Z or Beyonce.
Yeah.
I used to like Jay-Z music like 10 years ago.
Does not like Jay-Z.
I mean, like I respect Beyonce, but I think it is hilarious how like you can't dislike Beyonce or people hate you. I don't dislike Beyonce. I'm kind of neutral on her. I did like that one song. What was that song she did? Everybody got hated on her for. Not Single Ladies. That one is fun to dance to though. But this is the most recent one, the one in New Orleans.
Oh, Formation?
Yeah, I
Oh,
like
that's a
that
great
one.
song.
Yeah, so that one I liked. So like that was like the first Beyonce song that I think I could say I like legitimately like really liked. I did kind of like Destiny's Child songs, but not anymore. But like back in the day, I did. Anyways, the systematic standard uncertainties are combined. So we have one from Nist, and then we have one from our measurement on my scale. So the systematic uncertainties are combined in the usual RSS way, although the calibration uncertainty clearly dominates. So the one from the standard here, this is the Nist one. This one's super tiny, right? So it essentially is negligible. So we end up with the 0.949 coming out of this, which makes sense. The measurement sample of size m equals 23 of an object with unknown mass m is then performed with the calibrated scale. Okay, so now we have a scale that's calibrated. So this was all just for the calibration, right? We have the Nist, 10 kilograms. We stuck it on there and we measured it, and then we adjusted our calibration. But there was some uncertainty introduced by that, right? Because we adjusted it by an amount that we had to measure the offset, right? So we measured this mean offset to be 10.5 kilograms. So 0.5 kilograms, like my scale and my measurement process went into that. So I introduced some uncertainty beyond the Nist thing, and that's what actually what dominated this, was that our uncertainty we introduced when we calibrated it. So just because you calibrate it doesn't mean it goes away. That systematic uncertainty is still there. It's just hopefully significantly reduced, which it is, because it was going to be 0.5 kilograms, which is way bigger than 0.09. So, okay.
Cool.
So a measurement sample of size 23 of an object with unknown mass m is then performed with the calibrated scale. So now we're going to use the scale. So it's calibrated now. There's some uncertainty. Now we're going to use it with 23 sample size of 23 to measure the weight of an object. The sample mean is 9.04 kilograms, and sample standard deviation is 1 kilogram. How confident can we be in the result?
95%.
95%. Certainly both the systematic and random uncertainties must contribute, right? Before we can consider their combined effect, let's compute the standard random uncertainty. So the standard deviation of the means here is going to be the standard deviation divided by the square root of sample size, right? So 0.209 kilograms. We can combine the systematic and standard uncertainties in the usual RSS way. So we do, and we get 0.23 kilograms. Since these are standard uncertainties, we must find its effective degree of freedom nu before assigning it a confidence with a student t-score, right? So these are the one standard deviation ones. How can we estimate this from these different sources of uncertainty, each of which has their own degree of freedom, right? Because one had 23, one had 10, and some had infinite, right? The one we got from Nist was just handed down from God himself. So we assume that they had a large degree of freedom, large sample. So infinite, 23, and 10. And so we have to estimate what our nu is, what our degree of freedom is in this value. Okay? A method of estimating the effective degree of freedom is given in the textbook and is presented in an equivalent form here. I actually don't really like their equation. I'll explain why. Let a measurement have j random standard uncertainties, Sj, with corresponding degrees of freedom, nu Sj. Further, let it have k systematic uncertainties, Bk, with corresponding degrees of freedom, nu Bk, with the effective degree of freedom, then the effective degree of freedom is, according to this estimate, this expression. Which the book has a little bit different. It doesn't break out the index into two different, the standard versus the systematic versus the random. It has one index, and it seems to imply that every single measurement has a known systematic and random uncertainty associated with it. And I think that that's really misleading, and it kind of confuses people and makes it so that they can't use this equation, this formula. So I changed it a little bit so that it was clear that you just take all your random uncertainties, S's, and you take all of your systematic uncertainties, your B's, and you combine them in this way with their associated nus, and this is the estimate. So we'll do this now. So from above, we have j equals 1 and k equals 2, meaning there's only one of these random standard uncertainties, and that was the one that we just computed right here. Okay. And k equals 2, meaning that we have two systematic uncertainties, two B's. So given in table 5.1. So I think 5.1 is... Oh, I didn't re-include it. I should have. No. Where did I put them? Anyways, it's back in table 5.1, which was unfortunately before this. Oh yeah, no, I feel like this was just wrong. We have, in standard uncertainties, we have S associated with the calibration. So, S associated with this, right? So this was just our one S. That's all we had was just this S. And then we had the B associated with the standard that Nist gave us, and then we had B associated with the calibration. Right? Those were our three standard uncertainties. So there are two B's, which makes K equal to 2, and then there's one S, which makes J equal to 1. And if you plug those in here, this gives nu equals 29. So this had nu, so I'll list the nu values. For S, nu is equal to m minus 1, right? Which was 23, so m was 23, so we've got 22. B, this came from Nist, right? We assume that they had just infinite number of samples. Greater than 30, we just assume, so just say infinite. And then B, calibration, we said it was 10, right? We had 10 samples. Was it 11, 10? Remember? N was 10, so we get 9. 10 minus 1 is 9, I think. So those are our news. We take the S's and the B's that we computed, and we plug them into this formula. We get out 29. That's close enough to 30. Remember, 30 is sort of the threshold for calling it large. 29 is good enough for government work. So we say that's large, and when we say it's large, we say it's essentially just a Gaussian, just a normal distribution. So instead of needing a t-score, we can just use a z-score. So if it's 30 or more, if n is 30 or more, or if the degree of freedom is 30 or more, we can just say, it's just Gaussian. So we can use a z-score, and we know that a 95% confidence level for a z-score is just 2 standard deviations. We can look it up in the table, but that's one I know off the top of my head. 95% is 2 standard deviations, 2 z-scores. So you could look it up if you want, but that in the t-value, if you did a t-value instead of a z-value, it would be very, very close to 2. So you multiply that by this combined standard uncertainty, and you get 0.459 kilograms. So our confidence, there's table 5.1. Jesus. Yeah, no wonder. But I did this. I just redid this over there. What do you know? So I was right. Table 5.1. I wavered. I thought I had a typo. You guys were sitting there like we knew the whole time. We just didn't say anything. But okay, so So that means that using 95% confidence uncertainty for our interval, our best estimate for the mass is that it's equal to the mean plus or minus our uncertainty, and we have a 95% confidence in that. So this is our final report. So our reported value, so if we put that 9, we just put some mass on the scale after we calibrated it, and we would report it as this: 9.04 plus or minus 0.459 kilograms with a 95% confidence. Okay. So now we'll do an extensive example. Consider a temperature measurement made with a linear calibrated temperature voltage transducer. The calibration data is given as Tcal in units Kelvin. Actually, I gave it in units C, but it doesn't really matter for this problem. And Vcal in units V. The measurement voltage sample is given as a time series VA in units volts versus time units seconds, where we can assume relatively constant measurement conditions and a stationary process.
I have a question.
Yeah, what's up?
Couldn't we have taken your goofy ass scale that was weighing 10.5 kilograms and the accuracy is plus or minus almost half a kilogram once we solve all of that stuff?
Mm-hmm.
Wouldn't the original scale have been with 95% confidence within that interval?
The answer is that was just an accident. Essentially, we got rid of the 0.5. The 0.5 was just an offset. And we can get rid of the 0.5 by calibrating it, right? So we got rid of it. So actually, the goofy scale was reading 0.5 kilograms off, right? But we adjusted it so it wasn't reading that off. Okay? So then what's the uncertainty? And this is still the answer.
Okay.
So try to. It's difficult, I think, sometimes to understand this uncertainty stuff. But I'll try to kind of give you.
Can't wait for this podcast.
So when you picked up the scale originally, you're like, I have no idea. I don't no idea how much confidence I have in what value it's reading, right? So you get yourself a nice standard, the Nist 10 kilogram. You stick it on there, you say, oh, okay, it's about 0.5 kilograms off, right? So you adjust it. So now it's reading 10 kilograms at 10 kilograms. But, of course, it's not perfect, and so you do some measurements, right? And they're going to vary a little bit about 10 kilograms. They're not going to be exact. Like you take it off, you put it back on, it comes out to be a little different. Take it off, put it back on, to be a little bit different, okay? So you take some samples, and there's a little bit of spread there. There's a little bit of spread in your measurement. So you measured it, but it still has a little spread to it. So the amount you calibrated it, you don't know exactly that it's 0.5. You know that it's 0.5 with a little bit of an interval around it, right? That was off. So that's where the uncertainty comes from. Not from the 0.5 that you moved it, but from the amount of spread in the value that you measured. So if I put it on the number line, then here's your 10. Here's your 10.5. When you were doing this calibration, you made measurements, and they showed up like clustered around 10.5. The average was 10.5, right?
Oh.
And so you just took the average and you just moved the average over to 10 by subtracting 0.5, which is great, but you still had this happening. You still have this spread around 10 then. So you still have some uncertainty. And it came from even just measuring what the offset was. So measuring this 10.5 introduced some uncertainty into your measurement, your final measurement, because you calibrated based on that measurement, right? So you move that down. You had some uncertainty based on the spread. There was also some uncertainty in that 10 kilogram, the Nist 10 kilogram came with its own 200 times 10 to the minus 9 uncertainty, right? So it came with its own uncertainty. So there's this uncertainty, which we called B standard. And then there's the uncertainty that you got in measuring 10.5, which we'll call, I'll call this B, and this I called it B cal. B cal. So those were two uncertainties. So in our table right here, we had B standard, the Nist one, and then the one we got from when we calibrated our scale. So those two. And then we measured another weight, like a totally different weight, okay? And it had its own spread. So we measured another weight, and it had a standard uncertainty of 0.209 kilograms. We took 22 values of it. Well, we took 23 values of it, right? And the spread, the standard deviation of the means was 0.209. So all three of these have introduced some uncertainty into the measurement, because these were readings that were taken on the scale that we calibrated with these things. So they're accumulating this uncertainty, right? And so that's why we have to combine them into this value. If we only wanted 68% confidence, we could have stuck to 0.23 kilograms. We wanted 95, so we moved up to 0.459. If we would have wanted 99.99, we would have had to go, our interval would be much larger. Does that make sense? Okay, cool. I know, it's just kind of a coincidence that the numbers came out to be, and you're like, but, we could just do that.
Just measure it.
It wasn't, yeah, I see what you mean, but it wasn't, it was just an accident. I try not to let the numbers look accidentally like it was just something, because I know we always are looking for shortcuts. But there was really no shortcut here. If there's one thing you learn from this class, it's that there are no shortcuts here. Okay, so let's do an extensive example in 5 minutes. Let me think.
You can do it.
No.
Those are the words of Batman. Yeah, what if you just read
You guys get it? I just went through it. Is that good?
That's good.
No, I think I'll wait and do. I think I'll wait and do it. It's actually kind of similar to what we just did, but it's a little more involved. You have to do we're going to be given calibration data in this case, and we're going to have to come up with the calibration curve. which, you know, for those of you in the lab might have had some experience with this. Learning how to deal with uncertainty in your calibration curve, we're going to learn how to quantify that as part of this example. So, yeah, any questions that we could maybe address in the last 5 minutes that are not this extensive example?
So, are we doing an in-class file?
Oh god, no.
Please have it in class now. 2 hours straight test.